Hello, everybody. Welcome to the Latin American webinar on physics. I'm Camilo Garcia-Celi from DESI in Hamburg, and I'll be your host today. This time, we have a very interesting talk by Laura López-Honorez, who will tell us about Higgs-coupled minimal dark matter. Laura is a permanent staff researcher at the Université Libre de Bruxelles in Belgium. Laura did her PhD in the same institution, but before obtaining her permanent position, she held postdoctoral positions in Universidad Autónoma de Madrid, the Max Planck Institute in Heidelberg in Germany, and at the Free University of Brussels. And okay, before we start the talk, I would like to encourage you to ask questions. You can do that by typing them in the designated box in YouTube, which you can find on the right-hand side of your screen. At the end of Laura's talk, I will read the questions loud. Thanks, Laura, for accepting the invitation to present your work. And please go ahead. Okay, now you have to share your screen with us.
I'm sorry, but I have no idea what is happening. So the screen is mine now?
Yeah, you have to click on the left
yes, okay.
corner.
So good. So anyway, thank you. So I understand, if I understand correctly, now everybody's supposed to see me. So hello, I'm Laura Lopez. I'm going to give you this seminar now, and I'm going to share my screen. So I think you won't see me after that. I hope everything is going to go well.
Yes, I think everything is going well so far.
Okay,
so
now
let's see paper.
I completely forgot to open in advance the thing, so let's go. Okay. Here you are. Okay. So thank you very much for being all there. Sorry for this beginning a bit chaotic. So I'm going to talk about, sorry?
No problem at all.
Okay, so I'm going to talk about Higgs-coupled minimal dark matter scenarios, and this is a work I've been doing in collaboration with Michel Tidgat, Brian Zaldivar, and Patelis Siveloglu. So let's first begin by describing what I mean by fermionic, to minimal Higgs dark matter models. So first there is minimal dark matter. So in the minimal dark matter scenario, you have, you need at least one component in the dark sector, which would be your dark matter, that talks to the standard model through a certain portal. And let's say that in minimal scenarios, you can have actually your dark matter that is made of, one single add to the standard model. That could be a Majorana fermion that talks to the standard model through the standard model gauge portal. So this is the idea of the so-called minimal dark matter scenarios, in which case you have fermionic dark matter. And in particular, it has been it's already well known in the literature that for fermionic dark matter scenarios, you typically end up with a possible triplet or a quintuplet as a good candidate for dark matter. If you just take the standard model plus this single Majorana multiplet, let's say the quintuplet, let me remind you that, so I assume that this beast has a Majorana mass as up there in my screen, and that the Majorana component includes, this fermionic quintuplet is composed of a neutral component that is going to be the potential dark matter candidate, and some charge component that actually are going to get a small mass splitting with the neutral component thanks to a gauge loop contributions. So at the end of the day, you end up with the neutral state that is going to be potentially the right dark matter candidate. And if you just go through your computation of the Relic abundance at this level, you end up with a potential triplet with a mass of 2.4 TeV as a good candidate, and a quintuplet with a mass of 4.4 TeV. Now, things are not so simple. In particular, when you are considering particles with such a large mass compared to the mass of the mediator, in this case the gauge bosons, actually the gauge bosons act as a very light mediator. And in this case, you can have actually non-perturbative effect that enters into the game, known under the name of Sommerfeld effect. And also you can have, so I mean, this is what is represented here. You have multiple exchanges of a light mediator that are going to affect for example, the computation of the annihilation cross-section of your dark matter candidate into a standard model finite state. And you can also have actually bound state formation with the emission of a vector boson, in particular a photon, and some bound state that is also, I mean, that potentially can also affect your dark matter Relic abundance computation. In the case of the triplets, it's mainly Sommerfeld effect that plays a role. You go from a mass of 2.4 TeV to 3 TeV when you take into account all these effects. For a quintuplet, there is a recent paper of Libre and collaborator, which have been computing the effect from this 4 TeV approximately to the Sommerfeld enhancement case, to which goes up to about 9.5 TeV. And then on the top of this, you have bound state formation that can brings your dark matter quintuplet with a Relic abundance, which accounts for all the dark matter in the universe with a mass of 11.5 TeV. The question now is this minimal dark matter scenario constrained? It is constrained, and actually constraints can be very strong, especially when you look at indirect detection searches for dark matter. So here in this plot, the annihilation cross-section is shown for a quintuplet scenario obtained in this paper as a function of the mass of the quintuplet. So as I just said, you expect, taking into account bound state formation, your quintuplets that give rise to all the dark matter to be in this window, in this green window. Shown in this plot, you have also the typical annihilation cross-section for annihilation to WW and photon into photons. Actually, these here it seems that the constraints are a bit far away from the cross-section itself. But if you look at the latest constraints from the Hess collaboration, a paper of Rinchiusu, sorry for my not good pronunciation, from ICSC 2017, they actually get to constrain the annihilation cross-section into gamma gamma up to cross-section of 10 to the minus 26 centimeter cube per second with gamma ray constraints from the galactic center. But this is with a Caspi profile. With more core profile, you can potentially evade these constraints. You have also a recent paper of Cuoco and collaborator for November 2017, where they look at cosmic ray constraints. And in this case, it seems even more difficult to evade, actually. Cosmic ray constraints in the case of quintuplet and triplet dark matter. At the level of direct detection, things are pretty much different, actually. You have, in this other plot of Iseno and collaborator from 2015, the scattering cross-section on nucleon as a function of dark matter mass. And this blue dots dashed line corresponds actually to a quintuplet dark matter, which do not depend much on the mass. So, I mean, you can go to higher mass and you still have the same cross-section. And you have to keep in mind that actually the constraints from Xenon 1 tom are actually higher up here. So this is not a cross-section that is going to be tested soon. So, I mean, at the end of the day, you have to keep in mind that fermionic dark matter, minimal dark matter scenarios is a possibility, but it might be excluded due to indirect detection searches. So the point here is actually to look a bit of what can we expect if we extend a bit this portal to the standard model, including X, so the standard model scalar. If you want to play with, with scalar dark matter, it's very easy to take this into account. For fermionic dark matter, you cannot just play with Majorana, a single Majorana candidate. You have to add 2 Weil fermions into the game. So I will go back to this, in the rest of the talk. For those who are already sick of this talk, I give you already the main message of this talk. So, the idea indeed is to include the Higgs into the game, into the portal. What we got as a main feature of this model is that at the end of the day, in these Higgs coupled fermionic minimal dark matter scenarios, you always end up with typically very compressed spectra between the neutral candidate that is going to play the role of the dark matter and the charged candidate, with typical mass differences for couplings of the order of 1 that are of the order of the GeV compared to the masses of the dark matter that are multi-TeV. An important point is, as I said in the previous case, you have to be very careful because non-perturbative effect change much the parameter space where you expect to have the right dark matter abundance. So this is something you definitely have to take into account playing with these kind of models. And at the end of the day, somehow you end up with some stuff that is, because of these compressed spectra, that are going to look like something that is a triplet or a quintuplet of SU2, and might actually be tested by direct dark matter sources due to their coupling to the Higgs. So, okay, let me go step by step now, and begin by the treatment of this Higgs coupled minimal dark matter scenario at perturbative 3 level first. So this is the picture I had before. As I just said, I want to include the H particle into the portal, and with fermionic dark matter, it means that I'm going to have to have not only a Majorana fermion but 2 Weil fermions to play this game. I'm going to have to introduce a Z2 symmetry for dark matter stability. So in the case of just minimal dark matter scenarios, the quintuplet is actually stable, but here I'm obliged to introduce a Z2 symmetry. For this combination, 1 Majorana plus 2 Weil fermion, this is something you have, it's a setup that you have already seen somewhere before. It's, for example, in supersymmetry. You have the singlet doublet, which is a binary Higgs system, the triplet doublet, it is a Wino Higgs system. Actually, you can go to higher representation. So here are the possibilities: singlet doublet, triplet doublet, those I just said. You can also consider the triplet quadruplet case combination, which has already been considered in the literature before, but not taking into account non-perturbative effects. And the quintuplet fourplet is another possibility that was not considered before. You can even go to higher representation, but in these as it has been typically done in these minimal scenarios, if you want to keep electroweak perturbativity until M Planck, or at least high energies, you don't go to a larger representation than the 5-plet, 4-plet. So here, somehow I'm going to try to give a general view of these Higgs coupled minimal dark matter scenarios, considering 4 models: singlet doublet, triplet 4-plet, and quintuplet 4-plet. Good. So what does my Lagrangian look like in this scenario? So it's in this Lagrangian you see here, I have the kinetic term, so which involve all the gauge interactions, Dirac term, these 2 Weil fermions, psi and psi tilde, Majorana fermion, Majorana mass, and 2 Yukawa couplings for the coupling of the 2 Weil fermion of opposite hypercharges. Good. So from this Lagrangian, you can actually extract a very generic mass pattern, which, generic in the sense that you always get the same result, whatever the model you are going to consider. And the main point, as I said before, is that at least when you just go to the custodial symmetry limit where you take Yukawa 1 equal Yukawa 2, you can directly see that you always, except in the singlet doublet case, have a neutral, the lightest neutral component. So you get a neutral component from one Weil fermion, a neutral component from another Weil fermion, and a neutral component from the Majorana. They mix together, so you have to, diagonalize the mass matrix. But at the end of the day, the lightest neutral component of the game is always going to be degenerate with at least the singly charged fermion, and maybe the doubly charged fermion in the higher representation. But this is in the exact custodial symmetry limit. So this, for example, if I look at the quintuplet, fourplet model, I show the masses of the different components of this game as a function of the Yukawa. This is Yukawa 2, okay, I vary on Yukawa 2. And this is Yukawa 1, which is equal to 1. So the custodial symmetry limit is here, for example, okay? I see that at Yukawa 2 equal Yukawa 1 equal 1, okay? I have actually the neutral, singly charged, and doubly charged particles that are completely degenerate in mass here. At Yukawa 2 equal minus Yukawa 1, so this point, I see the continuous green line that is degenerate with the dashed black line, which means that actually the neutral component is completely degenerate with the singly charged component. So, okay, this is at the custodial points, right? Now, if I go further from these points, just by eye here, you see that you always have very degenerate spectra. Actually, the mass difference between the lightest neutral component and the singly charged component is always going to go as the Yukawa coupling entering into the game, to the square root to the fourth. The VEV of the Standard Model Higgs divided by the mass of the heavy component in the story, the Majorana or the direct. At the end of the day, this corresponds for Yukawa of order 1 to mass differences of the order of the GeV for, this kind of scenarios. So the message here is that the neutral component is always, at 3 level at least, the lightest, and get a rather compressed spectra. So small mass differences with at least one charged component. This is another way of, giving you the results for all cases. So all models, singlet doublet, triplet quadruplet, quintuplet quadruplet. What we want to say here is that at the end of the day, these combinations always appear to split into singlet, triplet, and quintuplet combinations, and that the neutral component is always going to be either in a singlet, a triplet, or a quintuplet at these custodial points. So this is shown for the quintuplet quadruplet, but you find this generic situation in all the models that we consider. Okay, now let me go to the case, to what do we expect as the parameter space for, in this scenario, for the lightest component to be the dark matter, what is the typical mass we expect for this dark matter candidate. When I have a single dark matter, the minimal dark matter model, okay, let's say just the quintuplet or just the triplet or whatever, my annihilation cross section always goes as alpha 2 to the square, okay, electroweak coupling to the square, divided by the mass of the dark matter squared, okay, just in the, let's say, SU2 symmetric limit. I forget about the gauge Boson masses. You have some prefactor here that depends on the representation of the multiplet, and an n squared for the dimension of the multiplet that comes into the game. But okay, so these are somehow the limiting cases I have here in my Higgs coupled minimal dark matter scenarios, in the sense that when the Yukawa are very small, and let's say the mass of the Dirac component here is very high, I expect to recover the minimal dark matter scenario with just the Majorana dark matter candidate. In the case of, for example, the 5-plet, 4-plet combination, if I consider very high Dirac masses, I should recover the pure 5-plet case. Remember, at the perturbative level, I had 4.4 TeV. In the same way, if I consider very high Majorana masses, okay, small Yukawa couplings, I expect to recover something, I mean, the Majorana completely decoupled, I expect to recover something that looks like a pure 4-plet, and the pure 4-plet actually has a mass around 2.3 TeV to give all the Relic abundance, where you forget about the fact that this could give a too strong direct detection signal. Okay, so now what happened when I mix these two guys? I mean, when I'm in this region, what happened there? How can I extract the limits of the viable parameter space for dark matter? Actually, it appears that, I mean, in considering very small Yukawa was small enough so that the Majorana candidate and the Dirac candidate are talking to each other, but where still the annihilation effect and co-annihilation effect are completely driven by gauge interaction. So by this type of annihilation cross section, I end up with an effective annihilation cross section that takes this form. I mean, this is just the sum of annihilation cross section where I take into account all the degrees of freedom and the relative mass difference between them. This is just the Grist-Seckel typical computation of co-annihilating dark matter cases. If I take this formula into account, I just get as boundaries, I mean, where I expect to have the right Relic abundance in this situation is the red line here. Okay, I expect that when I take into account the possibility to have a non-negligible Yukawa, I'm going to add up interaction. I end up in this. Should end up in this ballpark for the 5M4D model. And actually, this is what we expect, the red contour, and this is what we get inputting the 5M4D Majorana 5-plet with 2 4-plet Weil fermions. If I put this into this public code micromegas and I try to do a scan in order to get the typical scenario that are going to give me the right Relic abundance, I end up with this exact form I obtained before. The red line, the red dashed line, that is on the border there, is the same red line I had here before. Oh, sorry. Okay. Sorry, computer is slow. I go back. Okay. So in this region here, you see that I have, I go from blue to green to yellow colors that corresponds to larger values of the Yukawa. The boundaries corresponds indeed to the lowest values of the Yukawa, smaller than 0.5. So, and okay, so I just confirm the guess we could obtain just using Grist-Seckel like formula, taking into account gauge on the interactions. This is how the picture can be enlarged to other Higgs minimal coupled dark matter scenarios. So the 4-plet, 5-plet is here. 3-plet, 4-plet in green is here. You see it with, yes, here. The doublet, 3-plet is in the region here, so all the blue region that is allowed, and the singlet doublet is actually in the gray region that goes in that direction. So this is the region that are going to give rise to the right Relic abundance, making use of this, I mean, very simple formula, taking into account mainly gauge interaction and assuming that these particles talk to each other due to the presence of non-negligible UKWs. Just to go back to the 5-plate, 4-plate model. So this I already said before. UKW smaller than 1, I'm in the envelope. UKW a bit larger, I can begin to populate the interior. I want to go from this picture, to this gradient of color corresponding to the UKWs to a gradient of color that correspond actually to the scattering cross-section on nucleon. So the scattering cross-section on nucleon at 3 level is completely going to be driven when UKWs are non-negligible by X exchange here, okay? What you see is that you typically get yellow colors corresponding to the highest value of the scattering cross-section on the diagonal here. It's actually very easy to check that this is exactly the region where you expect to have the highest scattering cross-section for the mass, the Majorana mass equal to the Dirac mass when you work in the custodial symmetry limit. Also, you see that you have the lowest value of the scattering cross-section nucleon where the UKWs were the smallest, so this is nothing special. And you have also some blue points here, some low value of the scattering cross-section here. Actually, you can check that these blue points correspond to cases where actually UKW 1 goes to minus UKW 2. And this is also something you can very easily work out, that this is just due to the exact form of the coupling of the dark matter to the Higgs here. So, okay, but this is at 3 levels, not taking into account the Sommerfeld correction. So let me go to this problematic now. So what we are going to use here is that given that we have seen that we anyway expect our dark matter to be in the multi-TV range, we are going to work in the SU2 symmetric limit, where actually the isospin is a good quantum number that is conserved in annihilation. In the latter case, actually, instead of having to compute a complicated set of this is going to simplify largely our computation of the Sommerfeld effect. So the only thing we have to compute at the end of the day is the long-range potential that are going to depend directly on the quadratic Casimir of the representation entering to the game. So here I have, for example, a quintuplet that is going to annihilate with the quintuplet. I do 5 times 5, and this corresponds to a sum of representation. Okay. I have the associated Casimir, quadratic Casimir that enter into the game and give me just the long-range potential entering into the game, and this allows me to compute the Sommerfeld corrections that I didn't show exactly here in this slide. I'm sorry. So once I have obtained the potential, the long-range potential, I can extract the Sommerfeld enhancement that just depend actually on this overall factor here. And the annihilation cross-section for, whatever representation of SU2 can be, very easily computed through this very simple formula where you have the isospin of the beast that enter into the game, that comes into the game here. Annihilation cross-section at perturbative level. I'm sorry, this slide is completely unclear. So let me just go to the next slide because it's going to be much more simple. So as I just said, we work in the multi-TV. We have dark matter in the multi-TV regime, and we consider the freezer to happen in the SU2 symmetric limit. So we have considered the combination of abelian-like Sommerfeld correction. And just in order to obtain that, we have just used, group theory decomposition, which was what is in substance enters into this formula. I'm really sorry for being so confused in explaining this. At the end of the day, So for any representation of SU2, doublet, triplet, quadruplet, and quintuplet, which are the representation I've been considered, so I consider just the pure cases here, and associated isospin representation of the pair of annihilating particles that enter into the game, okay, I can compute the relevant coupling that enters, let me go back, in the computation of this long-range potential due to the exchange of SU2 gauge bosons. From this, I can extract the Sommerfeld factors, okay, considering a Abelian-like Sommerfeld correction, where at the end of the day, the coupling that enters into the computation of your Sommerfeld correction is alpha 2 to the square multiplied by these numbers, okay? And this Sommerfeld factor multiplies each time a scattering cross-section for a given pair of a given isospin. So this is what's the entry here, okay? And the total annihilation cross-section for whatever representation can be seen as this sum over the isospin of the pair of annihilating particles that enters in this column. I hope I have not lost everybody. So, okay, at perturbative level, we can compute the total annihilation cross-section for a doublet, a triplet, a quadruplet, and a quintuplet. Remember, for triplet, I said was obtaining 2.4 TeV, a quintuplet 4.4, a quadruplet, for example, this has not been computed in literature before, as far as I know. Maybe yes, at perturbative level, yes, it's also 2.4 TeV. Now, if I take into account the Sommerfeld factor and the formula I was trying to explain before, I get to a dark matter that is going to give me all the dark matter abundance. For a triplet, for example, I go from 2.4 TeV to 3 TeV. For a quintuplet, I go from 4.4 TeV to 9.3 TeV. And remember, in the case of the quintuplet, you have an extra enhancement of the annihilation cross-section due to the presence of bond state formation that brings you to 11.5 TeV. Okay. The quadruplet, you go from 2.4 to 3.9 TeV. So this is the picture I had before. So the one I obtained considering that I have potentially a quadruplet that can co-annihilate with the quintuplet, so the red region, thanks to the presence of Yukawas, and I populate this considering non-negligible value of the Yukawas, okay? If I go to the picture when Sommerfeld enhancement enter into the game, I'm going to move my limiting case of the quadruplet and quintuplet, for example, to the quadruplet here and the quintuplet there, okay? And now I take into account the fact that they co-annihilate, and I should change completely my the boundaries of my variable parameter space, okay? So this is, at the end of the day, what I expect for the variable parameter space for my models containing a quadruplet, quintuplet model, okay? A model containing a quadruplet, triplet model, a doublet, triplet model with the blue colors, and a singlet doublet that didn't change much, not affected much by the Sommerfeld corrections. So let me just, I don't know how much time I have because I don't have any time here. But so let me just comment on the prospects for dark matter detection. So as I said before, moving to Sommerfeld correction, in this case at 3 level, you are, driven by this kind of diagrams for the scattering cross section of dark matter on nucleons. Given that you have a Yukawa coupling, you increase the sensitivity of Higgs coupled minimal dark matter scenario compared to minimal dark matter scenario, which has only loop contribution to this. So you can, definitively test these Higgs coupled model scenarios. So, this is the picture in the usual form of scattering cross-section as a function of the mass of the dark matter. The quadruplet mass in the perturbative case is here, quintuplet mass is here, and this is the scattering cross-section due to Higgs interaction. It's the the cloud of points that you have here. So you see that you have definitely already models that would be completely excluded by Xenon 110 if I could stop at particular level computation. Okay. Now, I mean, if I had to take into account the Sommerfeld effect, I move this black line to this red line, and this other black line to this other red line. So I completely shift the parameter space. But at the end of the day, we expect the general form of this cloud to be not to change. So meaning that the models in which the relevant coupling to the Higgs that depends directly on the Yukawas, large Yukawas are expected to give you, anyway, a stronger scattering cross-section up to a certain specific cases where the Yukawa 1 equal to the minus Yukawa 2. You have model that can be tested in the future by Xenon 110, but you still have model that can completely, evade these constraints. And at the end of the day, you get to the NLO correction computation. You should go to NLO correction computation where you, that have been, for example, in the case of minimal dark matter scenario, been obtained, and that we're getting to the 10 to the minus 46 centimeter square for the case of the quintuplet dark matter. For what concern indirect detection searches, so we have actually now a larger splitting than in the case of the pure minimal dark matter scenario. In the pure minimal dark matter scenario, it was hundreds of MeV. Here we can get to larger splitting. So this we expect anyway to change the Sommerfeld effect and potentially move the position of resonant peaks. We didn't go into this detail, but we expect that this could help into evade the strong current gamma ray constraint on these models. And finally, I'm considering collider searches of this scenario, even though there are multi-TeV in the multi-TeV range. Actually, you could test these guys, especially thanks to disappearing tracks when the splitting is small. So this is, among other things, a study that was done in a paper of Cirelli and collaborator for the triplet, for example, where they have shown that, multi-TeV dark matter candidate of this type could be tested at a 100 TeV collider, which is which is not the case right now. Right now, we can test this model up to some hundreds of GeV, which is way beyond this parameter space is concerned. So, as a conclusion, we have extended the non-viable parameter space of Higgs-coupled minimal dark matter scenarios with the 5-plet, 4-plet model that has never been considered in the past. Triplets, quadruplet models had been considered in the past, but not taking into account Sommerfeld correction. So this changes, this shifts the viable parameter space. In all cases, you have to be very careful. Sommerfeld correction are going to affect your viable parameter space and your expectation for dark matter detection. And so we argued that Higgs-coupled minimal dark matter scenarios could potentially evade indirect detection searches and definitely be tested by direct searches, which is nice. So thank you very much for your attention. And now I don't know what I have to do.
Thank you very much, Laura. Now it's time for questions. I guess I should start with the people in the audience. Does anybody have questions?
I have a couple of questions.
Okay.
Can you guys hear me?
Yes, I can hear you.
Okay, so Laura, thank you very much for the nice talk. So I have a question. So several times you discussed about bounds.
I don't know if you are talking, but I don't hear you.
Huh?
I don't hear you at all.
You can't hear me?
I was vaguely hearing Camilo, but so.
Laura, can you hear me? No, she cannot hear me. Laura?
Yes, but I hear you. I hear you are talking to me, but I don't understand anything you're saying.
So it's a matter of audio.
it's a completely, it's like, yeah, I don't understand anything.
Maybe I can write the question.
I think this is the huge connection. Really, really sorry. So you could hear me correctly? Segundo Skype. Sí.
Can you hear us now?
No, I hear.
Now? Bien.
Now I hear.
Okay, so I was wondering about bound state because you mentioned them several times. So I guess you were.
Oh God, I hear you, but you speak very, 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 very slowly.
Mierda.
No, it doesn't work. I'm sorry.
Can you check the chat, Laura? With the icon in.
Sorry?
Can you check the chat? Because the question is there.
The chat. And where is the chat?
Just in the icon about the screen share.
You mentioned several times bound states. I guess you're referring to metastable bound states, right? So this is the question of Nicolas Bernal?
Yes.
Okay, good. I'm really sorry. Okay. So, yes, I mean, this bound state, that's right. So, I mean, this is definitely not my expertise. So this is this paper of, there was a paper of Mitridel collaborator, and it was a paper of Tracy Slater on this topic, right? So they get these bound states, and indeed this bound state can decay, and you can get specific signature of the presence of these bound states. I mean, you can have specific lines at lower energies. So I don't know if this is the question. And I mean, they argue that this could give you an extra potential signature of these scenarios. But we didn't get into looking at that into the details. What we just did is to account for the fact that you have to consider a higher mass into the game. So from this, you can extract somehow the couplings that enter into the game that allows you to extract the borders of your variable parameter space. But for example, in the case of the quadruplet, one can expect that bound state formation could affect the abundance, but we did not, I mean, compute them explicitly. The point is that in order to do that, you would need to compute the typical energy of the bound state. So this we checked at least, and we have seen that the bound state energy in the case of the quadruplet is lower than in the case of the quintuplet. So this is already something that will imply that we will have less. Turn off the video. My God, how do I do that? Like this. So okay, I think I turned off the video. Another question. Okay, so I didn't answer to your question, Nicolas.
Yeah,
I'm sorry.
No, yes, thanks.
Sorry. So I mean, I just wanted to say that in the case of the quadruplet, we expect that we can have an effect of the bound state, but the effect should be intermediate between the case of the triplet and the quadruplet. Okay, in the sense that the questions are much smaller. The energy of the bound state is much smaller in the case of the triplet and intermediate in the case of the quadruplet. Widespin independent scattering cross-section independent on the dark matter mass. Oh, just because the dark matter mass is super high compared to the mass of the nucleus. Can you read it loud? So this is the usual thing you have.
Can you read the question aloud? I mean, the question is why
sorry.
is the spin independent scattering
cross-section? There was a question from Nicolas Bernal. that was asking me why is the spin-independent scattering cross-section independent of the dark matter mass in slide 2? And the answer is that, I mean, just given that the mass of the dark matter is super high compared to the mass of the nucleon, at the end of the day, this goes out of the question, out of the problem. Okay. Not to present everyone, otherwise you keep presenting. Okay. Okay.
Laura,
I'm really sorry for this mess.
Can you hear me?
I think I hear you. Still a bit of crack. No, now I don't hear you.
Oh, yeah, because I'm not talking. Now I can ask a question. Can you can you elaborate a bit more on the interior detection signals? Because you mentioned that the mass splittings are different than in the standard scenario. Can you explain that a bit more?
So, I mean, I'm not sure I understood your question, okay? But I'm just going to say what I have understood. So you said that, you mentioned at the end that mass splitting could affect the Sommerfeld corrections, right?
Yes, that's indeed a detection.
Okay.
Yeah.
Yes. So, I mean, at the end of the day, you get a strong enhancement of the. I mean, you get this Sommerfeld effect that get important when you have the mass splitting between your neutral dark matter candidate that is very near to that in mass is very near to the mass of the charge partners. Okay, so like this, you can go from the neutral to the charge partner, exchange several times the gauge boson, and then get to 2 photons, for example. Now, if the mass splitting is larger, this is not you are going to be this is not going to be so good. So this has been studied by Tracy Slater in 2009, okay? And there are 2 things that enters into the game. First, the bound state energy, First, the typical kinetic energy you have at hand compared to the typical mass differences you have, the typical splittings. So this is the first thing you have to compare. But the next things that enter into the game is to compare, to take into account the bound state, the bound state energy. And yeah, so at the end of the day, when you have, if you look at this paper of Tracy Slater to stop, if you can stop sharing your screen. Okay, sorry, I have no idea how to do that either. Okay, so, okay. So yes, so you can reduce, I'm sorry, I'm a bit lost between sharing my screen and so on. So yes, you can potentially evade, you can have a large important Sommerfeld enhancement when you have a large mass splitting between the dark matter and the partner that enters into the exchange of multiple gauge boson exchanges. And this has been studied by Tracy Slater in 2009 and another paper that I mentioned in my previous, in the last slide before the conclusion. And the point is that we didn't do this analysis because we have worked in the SU2 symmetric limit. Okay, so we just assumed that the mass splittings between the partners is 0. Okay, but definitively when you look at indirect detection sources, you should take into account these mass splittings, and we didn't do it explicitly, but we expect this for some value of the mass splittings compared to the bound state energy. That it should make an effect and allow to evade potentially. So we didn't compute it explicitly, but could help in evading indirect detection searches. I'm sorry.
Okay, can you hear me now?
Yes, now I hear you.
Okay, I think it was an issue with your screen. Okay, now I have more questions.
I'm really sorry. This is completely a mess.
It's relax. So, does anybody have more questions? Oh.
Well, yeah. Hello. I have a question. Can you hear me?
Yes.
Did you consider different signs for the Majorana mass and eventually the Higgsino mass or the other mass parameters? I'm asking because I know in the neutralino case, actually the sign of the masses of the Beano and Higgsino, or even a complex value for the Beano mass parameter, can have a strong effect on the couplings to the Higgs. So I don't know.
No, we didn't take this into account. So we have considered positive mass contribution, but we have, and this is something important when you want to extract the Sommerfeld correction, and when you want to compute this I mean, because we have been computing the annihilation cross section for a given isospin pair. Okay, if you want to go from the annihilation, and the way we did it is to compute. Okay, we had to go from the annihilation of a pair of particles of a given charge to a pair of particles of a given isospin. Okay, in order to go from one to another, we have been using Clebsch-Gordan, and if you want to do that properly, you have to take into account the fact that, I mean, you have some mass, I mean, sign that enters between that enters when you look at the mass term of the neutral component and the charge component. There are different signs there which are very important, but I don't think this is your question. So your question is, have we consider complex masses and so on, and this definitely we have not been taken into account. So well, you think it could help to do something interesting?
No, also the signs I was asking, but
no, the signs we have been taking them into account.
Okay, thank you.
The relative signs of the masses of the charged particles and the neutral particles, yes, but we have not been playing with the complex masses and so on.
Very good. Is there any other question?
Yes, I have a second one, well, another one.
Okay, go for it.
So, Laura, when you introduce this Higgs portal, so you also have to introduce Z2 symmetry by hand, right?
Yes. I hear you. No, like I'm really sorry. I mean, this beginning of questions was terrible. I'm really extremely sorry.
But when you put this Z2 symmetry by hand, you're not like destroying one of the nice features of this minimal dark matter?
Yes. Okay. So this I agree. I mean, but this is only good. I mean, I fully agree. I mean, we are not making something as beautiful as the quintuplet case, but I'm sorry, but the quintuplet is in serious trouble with the indirect detection searches, right? So.
Yeah.
Okay, so okay, I agree. We are destroying the nice feature of the minimal dark matter scenario in the sense of the quintuplet dark matter scenario. I agree, but at the end of the day, this guy somehow, I mean, as far as I understand from the studies of, I mean, this paper of Cuoco and this latest constraint from Hess, is in serious trouble. So okay.
Yeah, definitely. We know that. But I have a question. So, do you actually, I mean, in this sense, did you actually consider constraints from Landau poles in your work? I mean, for choosing your representations, did you take that into account?
Yes. So, I mean, this was, I mean, I cannot show this again because I don't want to go to share screen. But I mean, yes, in the table I showed at the beginning. So
yeah, I remember.
The effect on the Landau pole has been considered by Pantelis in particular, and in the case of the 4-plet, we were getting to a Landau pole at 10 to the 10 GeV, not much Planck mass, but I mean, so we stopped there, 5-plet, 4-plet.
I see. I have another question, and I'm a bit curious. You said that before Sommerfeld corrections, the triplet and the quadruplet have the same mass.
Yes.
Is that correct?
Yes, they have similar masses.
Is this a surprising coincidence?
I mean, this is a surprising coincidence. So the difference between the two is that one is a complex field. I mean, wait, no, not a complex. Okay, it's not equal to the. It's not self-conjugate. Okay, so you have an extra factor of 2. So if you didn't have the fact that one is Majorana and the other is Dirac, you would have a mass difference between the two. But given that one of them is not equal to its, it's not self-conjugate. Okay, you have an extra factor of 2 that you have to take into account in the annihilation cross section that really plays a role at the moment you compute the Relic abundance. Okay.
I see. Okay, so I mean, at the end of the day, it's not surprising.
I mean. Yeah, at the end of the day, it's numerology, I think, but it's just, I mean, they end up with the same mass just because one is self-conjugate and the other is not.
Okay. Does anybody have more questions? Because I have a long list here.
I have a last one.
okay.
So just out of curiosity, at the very end of your talk, it's slide 13 or something like this, you show the xenon limits till 14 or 13 TeV.
Yes.
So I guess what you're doing is you're just extrapolating their limits from, I don't know, I have seen their limits till 1 TeV or so. It's correct to do that? Are you allowed to do it?
I mean, did I really extrapolate? I don't remember. I mean, the latest paper of Xenon 1 ton, when they show the first limits, they don't show it up to there. I'm not sure anymore.
I think they typically show it till 1 or 2 TeVs. Well, maybe in the last paper they show it till super high masses, but
I think you can constrain high masses for sure. It's just an
I mean, I just see if I have continued the constraint. I mean, the limiting constraint. I've just extrapolated the dependence to higher masses because I mean, I just expect the same dependence due to the number density that is changing in the same way.
Mm-hmm.
So it's possible that one of the line I've extrapolated, but I wonder if the latest Xenon 1 ton constraint, so which was the continuous magenta line I had. I wonder if this is not exactly what I don't remember. I'm really sorry. I don't remember. But it's possible either I just extrapolated or I just assuming the same dependence just because of the number density that decreases in the same way.
Okay, thanks.
Okay. More questions? So
Camilo, you have more questions?
Yes. Well, actually, it was along the same lines, like along the same discussion of delay detection, because you show a scan with the
perturbative level.
Exactly, with the perturbative level, and then you argue that somehow, if you include this Sommerfeld effect, you will shift these lines to the right,
yes,
in the delay detection plot.
Yeah.
Do you also mean that the scan itself, I mean the points on the scatter plot, will move, and then therefore that will be, I mean, you will not constrain your points after Sommerfeld enhancement anymore?
Oy. So I'm not sure I understood okay. So I
mean, you can explain the plot again.
Yeah, so that was maybe a two. So in this plot, so I'm sorry, I'm not going to share my screen, but in the plot that was on slide 7, people can see my slide or not? The slide do not appear somewhere else.
No, we can't.
No, at the moment they cannot see it.
So I'm going to share my screen again.
Yeah, that's fine.
And then I will. Okay, I don't know how to make not shared anymore afterwards. So let's do the share. You see? No. So yeah. You see something?
Yeah, that's
okay.
Great.
So this was the plot. Okay, so scattering cross section as a function of the mass, and the scatter plot you see here is, I mean, only 3-level perturbative level using micromegas. Okay. What I'm sure of is that, I mean, you see that these two. So you have a bunch of points that are above the Xenon 1 ton limit. Okay. And so these points, right now, they are obtained at perturbative in the perturbative computation. And if I take into account Sommerfeld correction, I have not only to take into account Sommerfeld correction in this range due to the exchange of gauge boson, but also due to the exchange of the Higgs. Okay. And this makes the thing even more complicated. So I don't know for sure how these points are going to move. Okay. This is absolutely clear. Now, if I go to lower values of the scattering cross-section, you see that I typically end up, so for lower values of the Yukawa, I typically end up with models that are still viable and that are in between the pure 4-plet case and the pure quintuplet case. Okay, and that are populated in between thanks to the presence of non-negligible Yukawa coupling. So I cannot exclude the fact, okay, so I mean, what I expect is that definitively, okay, let me go to the next plot. I'm sorry. Let's see slide. Okay, good. So, I mean, even my own computer is going bad. I'm getting there, I'm sorry. Attack. Oh, my computer extremely slow. I hope you're still hearing me.
Can you maximize the window so that?
I'm just trying to, I mean, even on my own computer, I cannot get to the right side. It's super slow.
Laura,
Okay.
can it be because you
Yes?
have two Hangout windows open?
Ah,
That's why it's
I
so
don't
slow?
know.
Because you have the principal one
My
and
God.
next to it you have another one.
You are right. I have two Hangouts open. So let's try. Okay, so I mean, here is the, you still see my screen?
Yes.
Okay. So so this is what I wanted to say. So I have this, I mean, this is the ballpark where I expect to see the variable points right now, okay, at perturbative level between the 4-plet and the pure 4-plet and the pure 5-plet case, okay? So somehow I expect to have also these points to be somehow shifted. I don't know where exactly, but at least in this ballpark. I expect the variable dark matter scenarios in the case of Higgs coupled minimal dark matter scenario, taking into account the Sommerfeld corrections with the gauge coupling plus the Higgs coupling to end up here and to be potentially tested by Xeno. So I don't know if this is clearer now.
Yeah, it is clear. Yeah, of course, looking at the screen, it's much clearer.
Yeah.
Well, it's already 1 hour, and it was a very interesting talk. So I would like to thank you again, and I would also like to remind the people in the audience that they can subscribe to the YouTube channel and to follow us in Facebook and Twitter. And thank you very much again. And let's talk again in the next opportunity. Thank you.